All right. So we want to start on page 119. We're on question 27.1. Let me check if I'm on the board here. There. Tell me when I run out of board, Zoom people. Out there?
Right there.
Close enough. Okay. Start on page 119. We're on question. What was that? All right, finally ready to go. Sorry about all the delays there. Okay, so we have a circuit. I'm getting lazy, so I'm going to draw my batteries like this. This battery has a potential difference E. And there's a light bulb in this circuit, right? So in this case, and this is, I'm going to call this circuit 1. And the problem number is 27.1, if you're looking at that in the book, page 117. There's some resistance here, R. Are you guys able to make out the text in Zoom? Is that big enough?
Yeah, it's clear.
Great. All right, so in this case, we have one battery, one circuit element. What do we know about the voltage on this circuit element compared to the voltage of the battery? Same or different? Same. If this is 6 volts, this has 6 volts. Okay. Now, let's say I want to figure out the current. How much current is going to be flowing in this circuit? Does anybody remember an equation that might help us figure out current? What's that? I heard delta V equals IR. Sometimes I use uppercase, sometimes I use lowercase, so whatever. In this case, I is going to be, all right? Now, in this particular case, that's going to turn out to be, doesn't matter if I use upper or lower here, I probably should have used all the same, so let's just make them consistent here, all right? In this case, I'm going to say it's E over R. Maybe I want to do everything algebraically for right now. So I'm going to actually change this voltage from 6 volts to E, just so everything's algebraic. And now remind me, how do I get the power? Does anybody remember any equations for power? Poison, IV. So these are our kind of main equations that we're going to use today. All right, in this case, do you agree that's going to equal E squared over R? Take a look at it. E squared over R. So now, for this particular one, I'm going to run out of some room here, so I actually want to use this here. Oh, let's see if I can fit this in here. Let's put in some numbers for this particular case. Delta V, we said, is going to be 6.0 volts. The current is, well, let's just run it and see. So I'm going to let this run for a second and get hot. So remember that as it runs, the resistors tend to heat up. What generally happens to metal wire resistors as they heat up? What happens to the resistance? Should go up slightly. So as it heats up, we might see a little bit change in here. So let's assume this is now warmed up a little bit. Maybe it's not perfect. What are you getting for a current? Can you give me a current? 1.6 amps. All right. So out of all this, what's the power in particular for this circuit? What's the power? About
7.2.
7.2.
Is that right?
I times V. It's about 10, right? 1.666666666 is 1/6. Yeah, times 10. Whatever, it's about 9.6, right? What are the units?
Watts.
What?
Watts.
What? It's about 10 watts. So this is probably a 10-watt bulb because it's, yeah, anyways. All right, so this is going to be our reference. Now, which one of these quantities, voltage, current, or power, corresponds directly to the brightness of the bulb, or most directly? Power, brightness, power. I want you to think about that, okay? So this is circuit one. There's our numbers. So on Zoom, that's the numbers we're referencing here. So you don't really need to see them. All that matters is we're going to do a bunch of different circuits now and compare them to this one. All right. For example, are there any questions before we go on? We're looking at Ohm's law here and the power equation and just playing with it. All right. Now I've got two. I'm looking at circuit two. Right. In this case, and I'm going to turn this one off just so it's not cooking there. Right. I've got circuit two here. I've got two light bulbs. Are they in series or parallel here? Yeah. So there's, I don't know if you could see that on Zoom at all, but there's one light bulb here, one light bulb here. There's a switch here, and notice this switch is open. Both of these are open. What do you think should happen to these bulbs? What's your gut tell you? Are they going to be brighter, less bright? What do you think? Probably less bright because I've got more resistance. I should probably have less current and probably less power. Let's do the math. Circuit 2. So this is 27.2. Okay. All right. In this case, I've got a battery, same power supply. I'm going to see if we can cheat a little bit. In this particular case, we're assuming all these light bulbs are identical resistance. This might save us some time. We could do an equivalent circuit, but I don't want to. I want to avoid that if I can. In this case, if this has voltage E on it, the battery has voltage E, and these two resistors are in series, how much voltage do you think they have? Do you think they each have E, more than E, or less than E? They add up to E. Remember, in series, the voltage on this side should add up to the voltage of the battery. Well, if you had to guess, how much is each one of these going to take if they truly were identical? Half. So this is going to be E over 2. And same here. Are you okay with that? If not, we could run the equivalent circuit, right? We could combine these two into one resistor that has resistance 2R. And then we could get the current, and then we could bring it back. All right. In this case, do you agree I've basically doubled the resistance? If you double the resistance, what do you think is going to happen to the current? If you have the same voltage but twice as much resistance, how much current should you have? Half. So instead of having E over R, we're going to have E over 2R, right? Or 1/2 E over R. Is everybody okay with that? Are these blocking your view at all, or okay? I can move them up and down if we need to, all right? So, well, what does this tell you about the power? It's a fourth. So what does that tell us about the brightness of the bulbs? They should be a fourth as bright because there's a 1/2 and a 1/2, right? The power is equal to 1/4 E squared over R. Agreed? So before, our power was E squared over R for circuit 1. Well, let's look at them. Oh, what should the current reading? Is this at 6 volts?
It's on.
What's that?
It's on.
Thank you. Is it at 6?
6.1.
Sorry. Okay. Now, I want to be clear before I hit play on this, right? Before I close this switch, right now, both switches are open. The idea here is these batteries are pretty close to identical because I'm using power supplies and they're the same manufacturer. So the power supplies are pretty good. But these light bulbs themselves are not that identical. We predict how much current. Over here, we had 1.6 amps. How much do you think we should have in this one when I turn it on? .8. Do you agree? The original current was E over R, which was 1.6 amps. Now we have half of that. We expect 0.8. Now, before we do that, If you have less current, what do you think will happen to these bulbs in terms of temperature? Will they get more or less hot than this bulb? Less hot. Well, if it's less hot, what's going to happen to the resistance? Less. So then what's going to happen to the current? Slightly. It's going to be slightly more than half because they don't get as hot. There's not as much resistance. So let's see. Are they running?
Yeah.
Okay. Let's get there. So I don't know if you can see that. Clearly, it's less bright. Do you agree? Okay. And so, oh yeah, that looks a quarter brightness, don't you think? Exactly. Quarter brightness. Look at the current. It's not exactly half, is it? So this temperature thing is a huge factor in this real life. Remember that the math we do for theoretical circuits almost never matches reality exactly. It gives you a ballpark figure. Here, these particular light bulbs, this one must be carried a whole bunch more. It must be a lot warmer, and the resistance is significantly higher because we would actually expect 2.2 on that one, or only 0.8 on this one, however you want to look at it. What's going to happen when I throw this switch right here? Let me turn the lights back on. People on Zoom, are you able to see this okay?
Yeah, looks good.
Okay, all right. Now, look at problem 27.2. That's the same switch, right? When I drop that switch, what's going to happen? Okay, what's going to happen to the top one? Come on. There we go. Let's take a look. Ready? Does it look about the same as that? Is the current about the same as that? All right. So what's the deal here? I'm going to actually get out a meter. The idea here is this switch. What do you think? Does the switch have a lot of resistance or almost no resistance? Almost none. Okay. So what I'm going to do now is I'm actually going to measure the potential difference across the switch. And I am on the millivolt setting, millivolt. All right. So now I'm just going to get into here. Right? Can you read the number off there, Nick?
1.2.
1.2 millis, right? Wow, that's tiny. You can look at that too. That's crazy low. Yeah. So when 1.2. So we're seeing something extremely small in terms of millivolts. So I just want to try and explain what's going on here. When we put a switch in here and close it, it's like adding a wire right there. The idea here is I have measured the voltage across this with a voltmeter. And we found it's something like well, let's just round up. Let's just say it's 2 millivolts. To be clear, when I drop that switch, there's still a voltage across this. But it's so small, right? When I put that in parallel with this, these things in parallel share the same voltage. So if it's 2 millivolts across the switch itself, I can only get 2 millivolts across the bulb. That's not enough for it to light up. To be clear, most of the current is going to flow down here and take this red path, right? So the current is basically going to take this red track. I'm going to take this meter out of here for now. There's still going to be a tiny amount flowing this way. It's just so small, the light bulb doesn't light up. You've probably heard the phrase, current takes the path of least resistance. I don't like that phrase. Unless you add in a little disclaimer. I would say current takes the path of least resistance, and a tiny bit of current takes the other path too. Right? There's still a tiny trickle of current here. It's just so small it doesn't light up the bulb. Clear on that? I am only deliberating on that because that's going to be important later. All right. So, all right. I'm going to turn this off so I don't forget. Any questions about how this is basically a short circuit, right? We allowed this to create a short circuit in here. And so right now it has to go through both light bulbs. Right now, it doesn't have to go through this bulb. Some of it does, and most of it flows through there. So the current is able to flow through here. That allows us to reduce the net resistance, and we get brighter bulb. Okay? Questions on that? All right. Let's look at circuit 3 now. This is the series case. Let's look at circuit 3. I'm going to open it so I don't spoil the fun. Okay. Now I'm going to do circuit 3 right here. We've got a battery. We've got 2 light bulbs in parallel this time, right? Light bulbs are not the greatest resistors, are they? This heating adds a lot of confusion, but it allows us to see brightness. I think it's worth it. Hey, real quick, what's the voltage across each light bulb right now? E. They're both in parallel with the battery. I like to think of it like this. I have a giant strip of metal down here. I have a giant strip of metal up here, supernode, if you will. Now, in this case, I'm going to use numbers. This I'm going to call ground. Ground is a fancy word for 0 volt level. That's the 0 volt line. Up here, I have the 6 volt line, or E. This is the E volt line, right? Everything at this point is at voltage E. Well, look at the difference between this part and this part for this bulb. It's E. The difference for this part and this part is also E. So I got my voltages E. All right, what's my current going to be? If I know the voltage across this resistor, and I know Ohm's law, what am I going to get for current? E over R, same as this circuit, right? For each branch. What's the power going to be? E squared over R for each. So far, so good? All right. What's the power delivered by the battery going to be? What's that? Yeah, I know there's going to be some wattage. Let's say this is a 10 watt bulb and this is a 10 watt bulb, because that's pretty close to what they were over there, right? 10 watts. How many total watts do I need? 20. Right? If I'm going to light up 2 10 watters, I need 20 watts. So what's the total power? 2 E squared over R. You don't get something for free. Over in this circuit, we had a single battery, and we got this reference power of E squared over R. Now we've got 2 light bulbs in parallel. Well, the voltage is still E here, right? The voltage is still E. What's the current through this battery? Let's look. I got current coming this way, E over R. I got current coming this way, E over R. How much is going to spit into this branch? What's that? 2 E over R. Whoa. 2 is the new 3. The idea is at this spot right here, and I'm trying to draw as a dot. The idea is I have 1.6 amps coming in from one light bulb, 1.6 from the other. That's going to spit out here. It should be about 3.2 amps, right? If you're saying, where's I get, I'm just taking my reference number. We said the original circuit has about 1.6 amps. So I would expect to actually draw 3.2 amps. Look at this on the top. I could have 3.2 amps coming in, and I'd expect 1.6 amps to go down each circuit, right? This is actually a rule we're going to learn about next time in class called the junction rule. The amount of current flowing in is equal to the amount of current flowing out. Well, how are these bulbs going to compare in terms of brightness to circuit 1, our reference level? What do you think? They should be about the same. Do they look pretty similar? You think I would learn, but I don't. What's going to happen when I flip this switch right here? Let me ask you, when I flip this switch, am I changing the voltage? If I erase this, I wouldn't change the fact that this is still in parallel with this battery. So what's going to happen to the brightness here? There is a very, very subtle change. I don't know if you can see it. See it? However, if we had better wires, if these were not cheap wires, it would be so negligible, it would be very difficult to see. And already it's barely noticeable, right? So the idea is we don't expect a tremendous change. What about the total current? What's the number?
About 3-ish.
3-ish, right? So now let's, right? You could imagine if we could tweak these a little bit. I guess I would say it like this. These light bulbs are not all identical. What's that? Yeah, so it's probably this light bulb is not nearly identical to the other two. There's always manufacturing defects, right? So yeah, these light bulbs are very close to identical resistance. It's not perfect. That's all I want to say about it. Are you guys okay with that? You could go through and find a match set, but we get the idea. It's approximately correct. Remember, in real life, this is an issue that you have with real life circuits. Your components are never exactly the same. Remember when you measured those 10 resistors? Most of them were about the same, but maybe they're off in the tenths column, whatever. All right, so far so good. In this case, why is this useful for household wiring? I could turn on and off one light switch in one room without affecting the other one, right? So this is why your house is wired in parallel, not series, right? If we did it in series, you'd have to constantly be adjusting the voltage of your house. That would be annoying, right? To be clear, your house runs on AC power. It's a little different, but the same principle applies, right? The refrigerator is not affected by a light bulb. As we have seen, and perhaps you've seen this in real life, that barely noticeable flicker is there, and you've probably seen this in your house if you turn on a vacuum cleaner or something with a big motor in it. And so there, what's happening is, strictly speaking, there's a tiny bit of resistance in these wires too, right? And so when I change this by opening the circuit, I'm not only taking out this light bulb, but also all of this. And so the circuit's changing a little bit, right? And so these wires are not completely negligible, but they're probably negligible to at least the second decimal, right? And that's what you're noticing there. It's just barely, we can see it with our eye, but if you put a meter on there, it's pretty low. All right, ready for the next one? Circuit 4. All right, starting to get weird. And then I guess I'll keep this one here. I'm going to clean it up a little bit. You can go ahead and start figuring out the power delivered to each bulb in that circuit. Zoom land, you can see okay?
Yeah, looks good.
Okay. You just never know with the font size, right? Because I don't usually like to use the full board view, but I thought this would be good enough. You guys can see those light bulbs turning on and off?
Yeah, surprisingly, I can tell like when one's brighter than the other two, like everything like that.
Sweet. Right on. Okay. What are we gonna do in circuit 4? Thank you. All right, and so in this one, there's a battery here. And then there's 2 resistors real close here in series.
Correct.
Are those 1 and 2?
Yes. Switch clean.
Okay. So there's a switch right here, open initially. All right. Then there's another one over here. By the way, I did all this work in the solutions in color. So if I'm going a little fast for you, remember, you can have the solutions open too, and you can review these at home. But hopefully, I'm just trying to get as rapid as we can through these circuits to give you some intuition. All right. Now, in this case, was this number 1, 2, and 3? Okay. One of these bulbs, actually, you should know the voltage across all 3 bulbs instantly. Tell me the voltage across number 3 and why. It's E. You see that that's in parallel with the battery here? So this is E. What's the current going to be? If I know the voltage is E, tell me the current. E over R for that one. What's the power? E squared over R. It's basically circuit 1, is it not? Exactly the same. What about this branch? That's equivalent to which circuit? Circuit 2. Because isn't this voltage to this E? And then because these are identical, aren't each of these E over 2? And then what about the current? And then the power is going to be 1/4, right? Right? Sorry, that's a little sloppy. I didn't write down all these for the other one because I'm running out of room, but do you agree the lower bulb would be identical to 1? Now, in this case, what's the current through the battery going to be? How much current is flowing through this wire? 1/2 E over R. You don't add the currents. The voltages add up, but it's the same pipe. Think of current as water flow. If I said 16 gallons per minute were flowing through the top, you'd be like, well, dude, I know it's 16 gallons per minute in this part of the pipe as well. So the idea is the currents, right? We don't add them up like we do the powers, right? The total power, you add up each term, right? So the total power total would equal I, whoops, sorry. Let me rephrase that. Power 1 plus power 2 plus power 3. The total power is sum them. Can you even see that at all, Nick? Are you good or no? All right. How about I do that? Right? Might as well put this one down for a minute too, right? Is that better for right now?
Yeah.
Okay. Sorry about that. So the total power is right there. Now, in this case, the current, you don't add them up for each piece, you add them up for each branch. So the current will be add the current flow in this branch to the current flow in this branch, or like the water flow in this pipe plus the water flow in that pipe. So based off that, how much current do I have? 3/2 E over R. Well, originally, what did we have? 1.6. What is our expectation for the total current in this new one? About 2.5. right? Half of this is 0.8. 3 halves would be 2.4.
Yep.
Right? So we're expecting 2.4 amps-ish. Got it? Oh, look at this. Crappy switch. Huh. All right. The idea here is this. This is circuit 2, this is circuit 1. But now this switch is kind of crappy, so I'm just kind of, it's not making good contact unless whatever. We'll just do that. All right, so then what I can do is when I close this switch, what's going to happen? We'll shorten this one out, and now we're basically back to circuit 3. Is this circuit 3? 2 bulbs in parallel. All right, but let's forget about that for a minute. What's the total current? About 2.5?
Yeah.
And that's kind of what we were expecting, right? Is this helping or not? Are you getting a feel for these circuits? You ready for the hard one now? Okay. All of these so far, there's been some trick we can do. I don't know if you noticed that. We could kind of guess our way to the voltages without knowing any rules. Well, look at the next one. Circuit 5, even I would not try to guess. In circuit 5, we're going to have 2 bulbs in parallel with another one in series. I don't immediately see a trick to just like guess the answer. I know how to guess the answer, but most of you would probably not, right? Just because I've done enough of these. So let's take a look at that one. All right. I think I can turn this one off for a little bit, just so I'm not. Okay, so what circuit did I say? Circuit 5. Okay. Right, in this case, there's a power supply here. There's a bulb here. Another bulb here. Then they come together, touch another bulb here. And then, how did I number them? Was this 1?
Bottom 2. You have switch to
On
3 below the top.
right here? I'll just, sorry, I gotta. Oh, I see. So there's a switch up here. Like that?
That's closed.
Oh, it's closed initially, sorry. Okay. Got it, got it. Okay, that's what we got, understood. Now, in this case, the combined resistance of 1 and 3, is that exactly equal to the resistance of 2? When I put these 2 in parallel, right, you see that 1 and 3 are in parallel? That's not going to be the same as resistor 2. Do you agree? Will it be more or less than resistor 2? If I add an extra resistor, should I have more or less resistance? Less. If you add resistors in series, resistance goes up. If you add resistors in parallel, this is counterintuitive, but I want you to think like this. Imagine I tried to force all this water through this pipe. All of a sudden I say, hey, you know what? I'll give you a second pipe. Wouldn't it actually be easier to pump water through the pipes if I had a second pipe? By adding a branch, it should be easier to pump current through this circuit. So in general, when you add a resistor in parallel, you're adding an extra path, which makes it easier. Think about it like this. If I have just this one pipe, let's say it's this cross-sectional area, then I add a second pipe, that's like doubling the area. I should get more current flow. It's easier to push water through the pipe. everybody okay with that? All right, so whatever. If this is resistance R, this is resistance R, and this is resistance R, this would be equivalent to a circuit like this, where this is number 2, that's resistance R. This is the combination of 1 and 3. What resistance will I get? If you double the cross-sectional area, shouldn't you get half the resistance? This is actually R over 2. If you want, you could say, look on page 117 in your notes really quick. On the left side, there's that trick. It says R13, if you're doing parallel, is R1 times R3 over R1 plus R3. Do you remember that rule? If you didn't see this, you could just say, dude, I'm going to use this formula and get it done. I'm cool with that. What's the total resistance overall? Is that still showing up on Zoom? Yeah, just barely squeezed it in there.
Yeah, it's right at the edge.
Like the weirdest looking circuits. But the idea is I'm just trying to compress this circuit down to here. I need this one big so we can write all the numbers in it, and those ones who cares. All right, so the idea is I'm using the basic series and parallel rules that we discussed for resistors. Well, now that I've got it down to a battery and one resistor, what do I know about this in terms of voltage? Cool. What do I know about the current? E over 3/2 R, which isn't that going to give me a 2/3? Is that cutting off on Zoom? Are you good?
I see the E over R.
All right, that's all we need. What's the power? Two-thirds E squared over R, because it's I times V. 2/3 E squared over R. Now, in this case, we know the current through the battery and the power delivered by the battery. Notice this is nice about the equivalent circuit. If I know that the resistance is equivalent to 3/2 R, I know the equivalent power load and current load required of the battery. So that's kind of cool. So just help me out. If we had 1.6 amps before, what are we expecting now for the current through the battery? 2/3 of 1.6.
1.2.
All right.
1.1.
How about we just punch it in on the calculator? I don't care. Do you? I have no shame. What's that? All right? What's the next digit? Just so I know. Is it 1.16? So 2 times 1.6 div 3. Oh, 1.066. Okay. So 1.07 amps. So remember, we're not going to get that number anyways, because it's a real life circuit. There's always imperfections between the light bulbs. The light bulbs are not all at the same temperature. Blah, 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 blah. We'd expect basically a little over an amp. Agreed? Here we go. Doesn't this look weird? Doesn't that look wrong? You're like, wait a minute, how is this light bulb lighting up? I'm doing this to prove to you the only way this could work is if there's current flowing through these bulbs. There's just not enough to light them up. Maybe we need to finish this calculation and see how much current really is flowing through here. But my guess is a lot less than through here. So let's go, whoops. I don't want to do that yet. So let's go through here. Let's work our way back. We got it, we got it, we're good. All right. Here, I did a series combination. Wasn't this a series combination? In series, things share the same. Let's remind ourselves. What parallel, what's the word I want you to always think of when I say parallel? Voltage. So if it's not parallel, it's series, it must be current or charge. Yeah, depending whether we're doing capacitors or resistors. Current, charge, related, same thing. So here, we got ourselves a 2/3 E over R here. Oh yeah, this thing's cooking. Well, this one is also. So now, what is the voltage on each of these? How do you get the voltage? Whose law? Ohm's law. It's V equals IR. Don't overthink. 2/3 E over R times R is how much? 2/3 E. Right? So how much is left for this one? This one has 2/3 of the voltage, and they're in series. 1/3, or 2/3 times 1/2 is 1/3 E. Now, if you get really crazy, maybe drop some acid. You start to look at these 3's and E's and just be like, whoa, what's going on, man? The world's upside down and backwards. But maybe that's just me without any acid. I don't know. I don't know. We'll have to check that later. That's a homework assignment. All right. Yeah, we'll do that. Why is lab lasting 35 hours? Okay, anyways, all right. But no, the point of this was, this is how you could have seen it and known it in your head. You could have been like, look, I know these two are identical. They're in parallel. That's going to cut the resistance in half. And then I could tell this is R over 2. This is 2R over 2. This is 2/3 of the total resistance, and this is 1/3 of the total resistance in series. And I could have guessed these two numbers right there like that. That's called the voltage divider equation. We'll revisit that later. But in general, if you have two resistors in series, we could do a trick where you say, okay, just take the ratio of the resistances and the voltages are opposite those, right? Or actually, sorry, the same as these, right? This is 2/3 of the resistance. I have 2/3 of the voltage. 1/3 of the resistance, 1/3 of the resistance. Okay. At this point, I can come back to here. I'm really interested in the power and the current in these light bulbs. So what do I need to bring back here? This was a parallel combination. Bring back the voltage. So this is 1/3 E. What's the current then? If I know this voltage is 1/3 E and this resistor is R, what's the current? V over R. One-third E over R, right? All I'm doing is I'm just using this. You give me the voltage across a resistor and you give me the resistance of that resistor, I'll spit out the current every time. What's the power? 190. This is why we don't see those bulbs lighting up. There's some current flowing through them. In particular, we know if the total is about this, we're expecting about a 1/2 amp through each of these. So we would expect, in this case, I'm just going to round this. This is about 0.5 amps. This is about 0.5 amps. And then we expect them to combine and spit out and push out at least about an amp, right? Again, it's not exactly true, is it? What's the number of amps we get for the total? What is it? 1.4. So clearly the issue here is these two bulbs are not getting warm. That means their resistance is awfully low. And that means we're getting an artificially high value of the current here. Are you starting to feel the intuition a little bit? what's going to happen when I close this switch? Oh, look, if I turn this off, I'm going to do this. I want to see if you can buy into this here. I know it's tough. Let me do this. Hold on. I think you might be. Give me a sec. You see it lighting up ever so slightly there?
Yeah.
It is there. Now this one's probably so dim you can't see it, right? The bulb is really hot and burning my hand with the science. Can you see okay?
Yeah.
All right. Hopefully you can see that bulb is ever so slightly lit, but with this one on, you can't. This is always fun too, to just torture people. I'm looking at you. You! All right. Okay. Now, how can we turn this into an exam question? There's got to be some way to make it hard.
Already hard.
Yeah. Okay, it's going to be a long semester. All right. My question is this. By what factor does the brightness of bulb 2 or bulb 1 change as I change the switch? So now I need some room here. I'm gonna have to erase this stuff. So I apologize. Anybody questions about this side, this board? It's old stuff, all right? Okay. Question. This is how I would take this and make it into an exam question. I would say, by what factor does bulb 1 brightness change if switch opened? Because the switch was initially closed, right? Now, there's lots of ways you could do this. The first way is to be the genius and just kind of say, I can tell it's this number. That's convenient if you're a genius, but it doesn't work for the rest of us. So I want you to know what I mean by this. By what factor? Factor is equal to P prime over P, meaning P after to P before. This is what I'm saying. So don't overthink it. If I ask you for by what factor, I'm just saying take the ratio. If that wasn't obvious, now you know what I meant. Factor of change is the same thing as ratio of final to initial. Got it?
Yeah.
So now in this case, we're going to have to think. I think we know one of these things, right? If we're doing bulb 1, right? Bulb 1 was 1/9 E squared over R. Agreed? When I open this switch, what circuit does this become? When I open the switch, what do we get? A series circuit. Which one was that? When switch opened, do you agree? We're basically getting this plus minus, and let me get this out of here, out of the way for a sec. It's basically when the switch is open, this resistor is gone. And now you know why I numbered them this way. Circuit 2, I believe, is the circuit. You agree? What was the power in circuit 2 of each bulb? Wasn't it 1/4? We figured this out already. The power was equal to 1/4 E squared over R. So now I'm going to drop that into here. What drops out? E squared over R, right? What is the answer? 9/4. Multiply both by the reciprocal. It's just 9/4. Now, it's not double, is it? It's close. It's 2.25. Right? So the idea here is, in general, the procedure that I just showed you helps us understand the brightness of this bulb goes up by more than double. Right? It goes up by factor 9/4. To be clear, what's happening to the brightness of the lower bulb? How about if we did the same equation for bulb 2? Would it get brighter or less bright? Right, take a look at the brightness. Right, as I open this, it dims. What would you expect to be true for the factor? Positive, negative, bigger than 1, less than 1. What do you think? It's not getting brighter, it's getting less bright. Is the power ever going to be negative? No. It's a negative % change, but the factor is less than 1. This is the trick. So when we think about this factor, if something gets brighter, the factor should be greater than 1. If something gets less bright, the factor should be a fraction less than 1. So in particular, it would be the power of this bulb is, oh my gosh, this is going to be 4/9 divided by 1/9. Wait, oh no, it's 1/9 divided by 4/9. So it's going to end up being something like 1/4. Take a look at it. It gets 1/4 of the brightness, something like that. Oh yeah, that looks like a 4. I don't know. You could do the calculation. It's always dangerous to try and do it in your head. That's what I'm trying to tell you not to do, and I shouldn't. Let me just do it real quick. Power 2 prime over power 2. Right? What was that? IV, is that 4/9 E squared over R? 4/9 E squared over R. And then in the end, it's 1/4, just the same as this one. Oh man, this is going to be something weird, isn't it? What do you get? 9/16. See, this is what happens if you try to do stuff in your head. It's almost cut in half, but not quite. Oh yeah, that's almost a half, not a 4. Good. What do you think? So far, so good? All right. Now I want to show you a couple of weird things. Now, before I show you this, I think it's important that I clarify a safety issue. Now, normally, in the old days, I used to do these with batteries. Now, the thing I didn't like about this was twofold. One, you didn't get to read the amps, so there was no measurement. This one was a quick way to get the measurement. The other thing is, when you recharge these things, they're never going to be exactly the same as each other. So I could get these things more precisely equal to each other. Right, to 2 sig figs. Oops. Always drifting a little bit too, right? But this is 6 volts, 0.0, 6.0, so I know they're very close to each other, right? All right, now I'm going to start messing around with these. Let's get this one out of here too. And what did I want to do? I think is circuit 6 next. You don't need to take notes on this, all right? Flip the page though and look at it. The idea is I want to connect both batteries to the same, and this is where you need to be careful. I'm going to connect one of these here. I would like to remind you that these battery replacements or power supplies are plugged into the wall. Now, I need to draw something. You don't need to draw anything. Okay, hold on. This is practical circuit knowledge to prevent damage, all right? The idea here is I've got a circuit and I want to put a power supply right here and I want to put another one on top of it right there. In general, this is a bad idea. And I'll explain why. There's a lot you can learn from this problem, but you don't need to write anything down. Aren't these plugged into the wall? Huh. What's the deal with this? Why do we have so many prongs here? Oh yeah, there's a big capacitor in there. Yeah, so did you see it stay on after I unplug it? Yeah, so keep in mind, these power supplies are pretty, they're designed to handle massive currents, and so you don't want them to instantly shut off. All right, so what are the plugs for again? You guys know what the different ground, there's a ground on this. What does that mean? That's the one that we want to talk about. Batteries don't have a ground, do they? Here's the deal. I plug this one in. This is ground. I'm going to go to numbers now. This means this spot in the circuit is at 0 volts everywhere across here. What is the change in voltage across this one? What is it? 6.0, right? So once I get to this spot, the voltage is 6. This one's also 6.0 for a delta V. What's the voltage at the top? What is it? 12. So the idea here is, this is why I've been using delta V's all along. This battery changes the voltage level in the circuit by 6. If I stick another one on there, where we're going to run into trouble is this is also connected to ground. But that means it's also connected down here. How much resistance do you see? Some or none? How about almost none, right? There's the wire itself. You're going to have 6 volts across here with almost no resistance. Not good. We do not want that connected to ground on the other one. So that's why I'm going to take one of these. Now these, you've probably seen these before. It's those little gray plugs. Which one is which? This one? Okay. The idea here is this metal tab is designed to be screwed into the wall so that this is actually grounded. So if you've ever seen outlets that don't have the 3rd prong, this is getting more and more rare, which is a good thing. Some of them used to have the grounding. You'd literally bolt this onto the centerpiece of the electric socket. There's a screw in the center. But now this is generally not a safe thing to do. Sometimes these are called death plugs. I don't know why. Don't do this at home. All right, so the idea now is we're going to disconnect one of these power supplies from ground. When I do that and plug it in, I'm going to operate it in a safe way in this case, right? What I'm doing is I'm disconnecting this circuit from ground, this one power supply. The entire circuit is still grounded, right? And so I'm not worried about electrocuting myself because there's a ground reference right here. I know that one of these power supplies is grounded, and now this one is called floating. That breaks this connection to ground. This is now a safe circuit, all right? So you don't want to mess around with that unless you know what you're doing. So now in this case, I can now plug in this other power supply without worrying about a spurious ground loop. Now in this case, I don't know if you can see it, but let's go around the loop. Well, by symmetry, I have 12 total volts on this side. That means I have 12 volts here, right? What's the voltage in between, if you had to guess? 6. What's the delta V across this volt? What's the delta V across this one? And isn't this exactly the same as 2 copies of circuit 1? But there's a trade-off. The power in this, right? Somewhere. You guys see my green plug? Where is it? It's not the same green. With that darker green. Whatever. Yeah, I'm doing it. All right. So I don't know if you remember, the power here was E squared over R. Can you even see that?
Can see it faintly, but I know what it is.
Sorry, it's not green. Is that better?
Yeah, that's much more clear.
All right. So in this case, what is the advantage in a series set of batteries? This is what I wanted to get at. Well, do you agree, instead of just having 6 volts, we can crank up the voltage? Have you ever seen, like, inside a remote control or something like this, where you'll actually see like a chassis like this, and maybe there'll be something inside that looks like a spring right here, and then a spring right here, then there'll be a tab right here and a tab right here, and you're putting batteries in there like this. Sorry, this is a bad drawing. You know what I'm talking about? Now, in these circuits, what we're doing is usually these two are connected by a piece of metal. So these batteries would be in series. And so in this case, you take a 1.5 volt, another 1.5 volt, we would get a net voltage of 3.0 volts, which maybe is the power you need, or the voltage you need to make the circuit run. So the advantage of putting batteries in series is you get better voltage, right? So far, so good. All right. Now, gee, what do you think I'm going to do in the next one? And do you think it's going to be safe or dangerous? It's going to be dangerous. All right. This one's even more dangerous usually. All right. So, but if I do it right, I can do it safely because I know what I'm doing here. When I put them in parallel, you can take a second. This is circuit 7. I'm going to write this up on the other board. It's going to have the same kind of issues with grounding. And this one is particularly touchy to sig figs. I'm going to try to explain it. Whoops. Right. So, oh, there's that green. All right. Now, in this case, what are we doing? Do we have just one light bulb? Oh, I wonder what the advantage of this circuit would be. Now, in this circuit, we could actually have them both plugged into ground, because if I plug them into the wall, isn't this ground? And this ground? So we don't have a grounding issue here because both the batteries will be plugged into ground. Now, do you agree that these are only 2 sig figs, these 2 power supplies?
Yep.
So do you agree it might be possible that this one's at, say, like 5.97 volts? And this one might be at 6.03 volts, and we wouldn't know it? So the issue becomes, if these two aren't exactly at the same voltage, which we know they would never be, right? You can never get these dials perfectly. There's going to be a small dissimilarity here, and you could push current the wrong way through these loops. If I get them close enough, it should not be a big deal. But what you'll see is they're very sensitive. And when I turn these on, right, if they were exactly, if I happen to get them exactly at 6.000 volts, and this one exactly at 6.000 volts, what should be true, do you think, about the total current through each of them? If I had exactly the same voltage, they'd be exactly the same. So in practice, our issue is we're going to have dissimilar amounts of current, and one battery is going to try and charge the other one, which we don't want to do. But in this case, if this is all at 6 volts, shouldn't this voltage basically be 6 volts? And shouldn't this power be basically like circuit 1, right? Our I is going to be E over R. So we expect approximately 1.6 amps, assuming it's the same as all the others, which none of them are exactly the same. And our power is something like E squared over R. Well, now tell me what's happening here. If I have 1.6 amps going this way, how much should I have in each of these branches? 1.6 coming in, how much should be going up and over here if it's ideal? What's that? 0.8. We expect each battery to split the current, right? The idea is the current for this light bulb has to come from these two batteries. If they were exactly the same voltage, we'd expect them to split the current 50-50. In practice, that doesn't happen because sig fig rounding issues, we don't know that they're not at the same voltage. And watch how different they can be. Watch. This will be the time that it actually perfectly. Oh, I gotta plug them in. Right. All right. There's one of them. It should be lit up, right? We got about 1.6-ish.
Yep.
All right. When I close this one, what do you get? Are they both 0.8s? Isn't that crazy? Now look, I could, because that's what I'm talking about. You can't tell. They're off just slightly. And so as a result, we get different currents flowing each way. And one of them is trying to charge the other one. Now, if I tweak them just slightly, but look how sensitive it is. Hold on, let me breathe on it. Isn't that crazy how sensitive it is? Like I'm barely touching it. I'm like just, you don't even. Now, so this is what I want to point out about this. The total power is the same for this one light bulb with circuit one. What's the advantage we're getting? If these were both batteries, each battery is providing half the power. The batteries will last longer. So that's the advantage of wiring in parallel. In parallel, you get two batteries that'll last longer. Let's say you're driving around, you're van lifing because this world doesn't pay us enough to live. Right? So you could have extra car batteries so that your battery doesn't run out of juice when you're in the field. Right? You can have multiple batteries in parallel so that they drain slow. Got it? In series, you get more voltage. In parallel, you get more life. Longer life. All right. Let's take a break. Woo. Man, that's intense. All right. Taking a break. You get all that out there in Zoom land?
As much as I can absorb.
That's it. That's pretty crazy. Yeah, definitely break time. All right, we'll see you in 10 minutes. I got 6 o'clock on this clock. All right. Holy cow, that's a lot of circuits. I hope what we've been doing will also help you with your kind of capacitance understanding. We're really driving home that when can you use the voltage, and that's very similar. So I don't know. All right. There we go. All right. So now we'll go to our standard imaging here. I want to start on page 122. And up until now, everything's been pretty basic, right? There hasn't been a lot of weird stuff. So pages 122 and 123 start to show you some weird stuff and some applications and how this stuff can actually get a little bit tricky. I hope you're kind of feeling solid on a little bit. So now let's try and shake things up. Let's say you have a battery here. Actually, I could go farther left now. The idea is we're trying to pretend we can see inside a battery. All right. So inside this battery, and what problem did I say we're doing? 27 point what? 8? Yeah, that sounds right. The battery one? Yeah, thank you. The idea is inside of here, we're going to assume there's an ideal battery. I haven't really said this until now. Every battery that we've been looking at up to now has been ideal. By that, I mean no internal resistance. But we know from lab the other day, you may not have understood it, but we said that there was sometimes some internal resistance, little r. And there's some voltage E. And the idea is when you just have this battery sitting here like this and it's not connected to anything, and you measure the voltage across it, you're going to get voltage E. Why? If there's no current flowing through this internal resistance, it doesn't take up any of the voltage. It doesn't drop the voltage. However, as soon as you put it in a circuit, this resistor over here is called the load resistance. We're going to use that capital R. So this is sometimes called a load resistor, right? Because it's not internal. So this is the internal resistance. This is the load resistor. This is an ideal battery, just this part of it. Now we can actually see that the ideal battery and the real battery do not carry the same voltage because some of this is lost. Now in this particular circuit, is this a series circuit or is this a parallel circuit? Series. How can you tell? How many loops do you see? One loop. When you have a one loop circuit, it's always everything in series. So remember, a way that you can see series in real life circuits is if everything is in the same loop, it's all in series. Now, in this case, what's the total resistance? If you have two resistors in series, how do I get the equivalent resistance? What's that? Nope. Add them up. Remember, capacitors would be the one over in series. Resistors, you just add them up. So resistors in series, that's like making them longer. L is in the numerator, row L over A, just add them up. All right. In this case, what would the current be? Well, it might help if I draw the equivalent circuit here. Right? The idea is this would be R plus little r. What's the voltage across that equivalent circuit? Now it's the ideal battery voltage across that. So what's the current? All right, E over R plus R. All right, that's fine. So now, because this was a series combination, isn't that the current everywhere in the loop? The same current right here too, right? Same loop. Now in this case, how much voltage is across each thing. So what's the voltage across this term? Is it?
Oh.
Voltage equals IR, does it not? V equals IR. Well, I know the current through this resistor. So the voltage is this current times this resistance. It's close to E, but it's not quite E. It's actually the ratio of this resistor to the entire resistance. Remember I told you that before? It was the voltage divider equation I alluded to. I'm like, oh, if you saw this cool trick, you could have known this answer. Remember the 1/3 and the 2/3 volts over there? All right. So in this case, here's something people forget, right? When you're using this equation, delta V equals IR, I want you to remember that the voltage across one particular resistor, how about I call this V1? The voltage across resistor 1 is the current through resistor 1 times the resistance of resistor 1. The idea here is the voltage is this current times this resistance. What's the voltage over here for this one? It would be this current, which happens to be the same, times this resistance. Little r over R plus R times E. Okay, does that make any sense or no? The idea here is, let me put some numbers on here, right? This is ground, so this would be at 0 volts. If I go from here, well, let's start over here. Ooh, this is tricky. This is tricky. Let's say I go from here. This is 0, right? All the way up to here. This spot would be at R over R plus, oh my gosh, let's stick in some numbers, all right? Let me just say this is at like 11 volts, okay? I'm making up some numbers. I apologize. Well, that could be at 11 volts. Now look, maybe down here, right at this spot, let's say this is a 12-volt battery. Well, then right here, this spot would actually be at -1 volt. Right? And then down here, I come back up to 0. So the idea here is this is a kind of a weird way to look at this circuit, but in this case, the voltage across the battery doesn't get truly displayed because you're losing some of it right here. We're losing a volt across this internal resistance. Now, this is exaggerating the thing, but remember in lab, when you had the circuit open, you got like 1.38 volts. And then when you closed it, you got 1.29 volts or 1.34 or something that was a little bit smaller. That's what's going on here. The idea is some of the voltage is lost against here. This would actually look a little bit easier to read if we didn't put ground at the bottom of the circuit. If I do this a little bit different, I think this would make more sense to you. Let's say I call this spot 0 volts. So if that's 0 volts, this spot would be at 12. This spot would be at 12. This one would be at 1 because I lost 11. And then this one right here would still be at 1. And the idea is I'd lose the last one going upwards to 0. So that probably makes a little bit more sense to you. So where you put ground in the circuit really matters. However, that's why these circuits were a little bit confusing when we use small resistors here. Look at the numbers. If you had an internal resistance of 5 ohms, which we saw was pretty typical, and if this resistor was 500 ohms, I hope you agree this 5 ohms in the denominator is pretty negligible, right? We'd expect this voltage to be 99% of the ideal voltage, and we wouldn't lose much across the internal resistance. Good enough on that? This is me trying to explain. If you want to understand this problem, right, you could look at 27.8 right now, or sorry, at home, and that will help you understand the lab that I just handed back, okay? Apologies for having to leave there. Now, I wanted to get to something else though. there's a power calculation. Right, I'm gonna get the power, IV. I'm gonna get, ugh. The power here is gonna be R E squared over R plus R squared. Let me see if that's right. Is that what you get?
Yeah.
Okay. So out of all this, this is the thing that I care about. I need to erase some stuff to make some space. So I'm going to erase some stuff. So right now, let's forget about all these numbers. Let's say we did some math here. We figured out all kinds of neat stuff. That's really cool. And right now, this is what we know. We know the current through this thing. And we know and I guess I could stick the voltage back up. We knew the voltage over here was something like capital R over R plus big R times E. And we use that to figure out the power through this resistor, just like we did in all those circuits before. My question now is, I want to maximize the power delivered to this resistor. If I want to maximize the power delivered to this resistor, how could I figure out what resistance I should use? So what resistance value should I use here to maximize the power transfer? You understand the question?
Yeah.
I want to make this power as big as possible. I'm going to do that by adjusting this resistance value. What do I do?
Make it close to 0.
Well, let's think. If you make this closer to 0, what happens to the voltage? Does it go up or down? It goes down. So if you decrease the resistance, the voltage drops to 0, the current goes up. If I increase this resistance, its voltage should go up, but its current's going to drop. Gosh, I just wish I could think there's got to be some way to figure out what value of resistance gives me maximum power. What's that? Derivatives. Good. One thing you could do, the easiest thing to do is plot the damn thing and look for the peak, right? But but what we should do as well is take the derivative. If I want maximum power transfer with respect to resistance R, Nick, take it away. Tell me what I need to do next. Tell me what to write. I almost failed Calc 2. That doesn't help. Sorry, I thought it would. All right, somebody else, tell me what I need to do. Derivative of what?
Power with respect to R.
All right, there we go. Now you're talking. Set it equal to, solve for. Got it? So this is a variation on something I could do. Right? So you get a power equation. This is very similar. It turns out the value you get when you do all the math is when R equals little r. The porridge is just right when these two happen to have identical resistance. Think about it. If these two have exactly the same resistance, they both get the same voltage, right? What happens here is if this resistor is larger than that one, it gets more voltage, but the current drops too much. If this one is smaller than that one, the current goes up, but this voltage drops so much. So the ideal happens to occur when these two are exactly the same. This is a variation on something that appears in an enormous number of branches of physics called impedance matching. I don't want to say much more about that because this isn't strictly impedance matching. It's similar to it, all right? But yeah, generally speaking, if you have okay, let's leave it at that. This has applications. I'm going to shut up. There's a comment about it there. It says impedance matching shows up in acoustics, optics, collisions in mechanics, blah, 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 blah. Okay. So far, so good? Let's look at 27.10. I'm gonna leave the rest of that for you to do, and making these plots, I think is worth doing, all right? 27.10. Ladder circuits. Now, these circuits at first seem absurd, as does my entire class, but that's something for another day. This could take all day. It goes on forever. It's infinitely long. And every single, it looks like a ladder turned on its side. You see that? It's a ladder circuit. Now, in this case, this goes on forever. At first glance, people think this is just something my teacher is doing to torture me. This just seems dumb. Turns out this has practical applications. The two that jump to my mind. These types of circuits appear in ADCs, or analog to digital converters. So if you're an electrical engineer, I guarantee you're going to see this. Now, the other thing that's interesting, this actually relates to cable TV. It sounds crazy, but you could imagine this would be, now I'm hand waving, serious hand wave. This is a serious hand wave signal, okay? Imagine this is like the resistance of the lines to your home. And then this is the resistance of the device in your house, et cetera, repeated, et cetera, repeated. It's not exactly like this, okay? But the idea is 10,000 houses getting cable would look approximately infinitely long, right? And so this is not that absurd. It has practical applications. So let's take a look at it. What do I want to do here? I want to determine equivalent resistance. So now notice there's two parts here. One is if they both have the same resistance, and the one is if they have R1 is equal to R and R2 is equal to R, 2R. And I forget, I think the first version of this problem where one of them's R and one of them's 2R is the typical push-pull or whatever you see in I don't even know if I use that term right. I'm going to take that back. This relates to the analog to digital converter if you use these, one of those values, and I forget which one, so I don't care right now. All right, any ideas how you could get this? Any technique in the universe. The world is your oyster. What's that? What do you mean? Are these in series or parallel? R1 is in series with all of this. R2 is in parallel with all of this. This R1 is in series with all of this, right? Right? It's not something easy there. The world is your oyster. You can do anything. All I want is argue. Your boss comes to you and says, just tell me the equivalent resistance. What's one thing you could do, I guess?
Or the ones that are in series.
Okay. Adding up infinitely many is going to be pretty difficult. Can we think of an easier number to add up? How about 10 billion? You could do 10 billion. That'd be pretty close, right? And that's pretty tough. So maybe you could start with just one. And then add in the next one. And then add in the next one. And then add in the next one and watch the numbers. Over time, eventually, they'll approach some asymptotic value.
We calculate like a good chunk and plug them into Excel. Excel do it for me.
Aha, make a computer do this for you. And in fact, who's a CS major? Fools. Okay, how would you do this how would you do the process that I'm describing in a computer with a code? Okay, yeah, what's this particular type of relationship called? Or relation? When you start doing this and then it feeds into itself?
Recursion.
Yes. Recursion relation. This is a classic recursion relation problem from CS. So one technique you could do is code it and literally make the code do the recursion for you and stop when it stops changing in the nth digit, where n is however many you care about. If you need this to 3 sig figs, just keep adding more branches until it stops changing in the 3rd sig fig. Tell the code to stop. Or you could do it in Excel and just keep plugging in more and more. There's got to be an easier way. This is the entire resistance. If it's infinitely long, isn't this also the entire resistance?
Yeah.
And that's, I think, where you were trying to go, right? Isn't this equivalent to a circuit that looks like, now I'm running out of room here, so I got to go spicy here. Right? Isn't this equivalent to a circuit that looks like this? The equivalent resistance is in parallel with R2. What? This is now an easy problem, is it not? The only weird part is, well, what's this combined resistance? Well, how about this? Do you agree the total resistance here should equal R1 plus this parallel combination?
Yeah. So
Good.
R1.
So whoops, R1 plus, what's the shortcut for parallel?
R2 times RE.
Right?
Yeah.
But wait, isn't our total REQ? Told you should have dropped acid. If you didn't do that, I can't help you. No. All right, so look at this. Isn't this crazy? The equivalent resistance is equal to something that has the equivalent resistance in it.
That's all.
Is it? What type of equation is this? Starts with Q. Quadratic. Multiply this across, don't you get RE squared terms?
Yeah.
Pop that over there. Don't forget REQ times R. I'm stopping the color coding because I don't care anymore. I'm living on the edge. I'm a wild and crazy guy. Isn't that a quadratic equation? I got an REQ squared. If you tell me the values of R1 and R2, I'm money. I got that all day. Here's a trick. Wait, I like that head shake. Are you good or you got it? Yeah, it's crazy, right? You could plug in 1 for this one and 2 for that one.
Yeah.
And then at the end, that would be in units of R. So you could find R. So literally you could plug in. So look at the first one. See how it says when R1 equals R and R2 equals 2R? The idea is you could literally plug in the number 2 here. You could plug in 2R, but why not just plug in 2? And R1, you could plug in the number 1. Is that a 2? Yeah. The idea is solve for this, and then REQ would equal some number with decimals, right? You just multiply that by R. Weird. I forget which one it is. It's either part A or part B. The answer is the golden ratio. Already on maps. Isn't that wild? Not on the test. All right. I feel it's important that you can kind of see this. Let's move on. Not on the test. All right. All right. I think that's cool. So that's like me throwing myself a bone. All right. I got to enjoy this class too. All right. But there, like I said, there's a few random applications. If you're an electrical engineer, you'll see it again. Phew. Why are we doing this? What's the point of all this that we're doing today? Do you remember? We're trying to get good at series and parallel resistance, right? Next time, we're going to handle what happens if we don't have series and parallel circuits. So I'll teach you a general technique for handling all these different circuits, even if they don't follow series and parallel. Today, we're trying to get good at series and parallel. To that end, I submit to you for your inspection this weird looking thing. What is this? No, this is a wire. Let's do this. I'm going to zoom in max here. Well, that's all you get. You can't really see this. If I get out of the way here. There we go. So it's basically a long skinny wire that's wrapped around a piece of ceramic. That piece of ceramic is a heat sink, right? A long skinny wire, when you run current through it, gets hot. I'm going to pass this around to you in a minute. Now there's a dial here. The idea here is, if I could, there's a little dial here, and we can connect at 3 different spots. One end of the wire, other end of the wire, and this leads to wherever I'm connecting right here. Look at 27.11. 27.11. I'm going to start this over here on this side. You can kind of see the 3 connections, and you just look at the wire. You can see it's a wire embedded. We're looking at, what did I say? 27.11. And I need to go back to this board. Come on. Oops. I need to erase. So look at 27.11. Get a head start on it. I'll be right there. Talk as much as you want. Get this rocking. 27.11. I'm on this board. All right, we're good to go. 27.11. There's a battery here. Then we've got this long skinny wire. You can literally see it. It's like the lab we did last week. And the only difference is the long skinny wire is wrapped around a piece of ceramic. And in addition to that, the top layer of the wire allows for electrical contact. We're going to take a resistor here, and I'm going to connect to it at some arbitrary point, as indicated by this arrowhead here. All right. Now, we're told that the total length of this wire is L. The total length is L, whereas this length is Y. We're told that this total resistance is lowercase r. This one over here is uppercase R. Is that right? Now, you know the resistance of the wire is rho L over area. You know that. We don't know what rho is for this. It's probably nichrome. We don't know the area though. But what we do know is the total resistance from the 2 ends is R. Well, what I want to know is what R top and R bottom are. To be clear, I want to know what the resistance of just this portion is versus the resistance of just this top portion. What does your gut tell you? The total length is L. I'm only using Y of it. The total resistance is R. What is it? Oh, you said rho Y over area? True. So how does that compare to resistance R? Let's not overthink it. If I wanted to compare them, what would Horatio do? Oh, this Horatio is pretty damn good. I like this Horatio guy. What drops out?
Everything from L and Y.
Okay. Right, so wait, you just told me that R over R top is equal to L over Y. Did I screw it up or is that okay? Basically, this is R,
Yeah.
right? So we're saying that R of the wire is just R. Right, so now, well, what's R top? Isn't it just the ratio of the lengths? If I use half of the length, isn't it half of the resistance? If I use a third of the length, it's a third of the resistance up top.
Yeah.
Does that make sense? So that's just saying take a ratio. If the length appears in the numerator, you just take a ratio of the lengths times it by the resistance. Got it? Thanks. Just in case it's worth. Trying to give these zoomers a hit off this. I don't know if you can see that at all. You see it at all?
It's pretty blurry, out of focus.
Good. All right, there we go. It looks like a. Does anybody know the name of this? You smoke it, it gets you high. Close. Pot. This is called a pot or a potentiometer. Right. Whatever. All right, so a variable resistor is another name for it. Sometimes there's old school ones called rheostats. Maybe you've heard of that term before, but whatever. All right, they're all subtle differences, but basically, we'll see why. But all right, it's called a potentiometer, related to the word potential. All right, let's see what we can get out of this. All right, so in this case, we know the resistance. What's this resistance going to be right down here in terms of R and Y and L? What's this length?
L minus Y.
L minus Y. So what do you think would be different? L minus Y over L times R. All right. So is everybody okay with these resistances now? I need some space. So I'm going to erase all that and I'm going to write these resistances in here just so I have them for reference. Okay. All right. So that was part A. So now we know that R on the bottom, we said was L minus Y over L times the total resistance of the wire. This one was just resistance of the top, and that's going to be just Y over L times the little resistor, right? Now, in this case, let's go to part B. Let's do this one in order. Let's get the equivalent resistance in terms of top, bottom, and R. Well, what's the REQ going to be?
1 over L that. 1 over L that.
No.
Oh.
Is everything in parallel here?
True.
No. What is in parallel?
R top.
Yeah. So do you agree it's going to be R bot plus the parallel combination? That would be the equivalent resistance. Right? It's this one plus those two in parallel. That's this one plus those two in parallel. That's the parallel shortcut rule. Do you see it? Is this okay? All right. Let's go to part C. Ooh. This is where it gets cool. Part C. So this was this part B? If Y is equal to L. If Y is equal to L, what happens to the resistors? Series or parallel? If Y is equal to L, where would I be connecting? At the very bottom, right? What does this look like? Series or parallel? Parallel. And that would mean R and R in parallel. Agreed? What's part D say? Y equals 0. What does it look like? Well, I know this one's here. Right? I'm connecting at the other end. What does that look like? Come on, where are you? This, isn't it? Kind of like that. You gotta, yeah, mirror it, but right? Isn't you this one basically shorted?
Yeah.
Remember that? It's all coming together. What voltage is across this one? How bright was this frickin' bulb when I short it? It's off. It's the voltage across the switch, which was 10 millivolts, remember? In this case, the voltage is approximately 0. It's in parallel with nothing, right? There's no voltage drop here. In reality, there's like, you know, a tiny fraction of an ohm associated with the wire in itself. So what does this device do? When you crank it one way, right? So in practice, this is what this would look like. There's a way you can connect here, a way you can connect here, and this was the tap into the center. So when you crank it all the way to this side, you get the full length of the wire here. When you crank it all the way back, oh my gosh, come on. When you crank it all the way back, you get this circuit. Notice in this circuit, how much voltage is across that resistor. 80. You just told me by turning this little dial, you can change the voltage from 0 to full. It's a freaking volume knob. It's what a potentiometer does. Isn't that cool? Practical applications. Now, in this case, do you agree we could go through a bunch of math and figure out the power here?
Yeah.
Now, to save you some time, oh man,
We're negative.
we're in negative time. All right, so the idea is take a look at those plots in your solutions. Okay. I took the time to make these plots for you, and they're in the solution so you can look at them. I was hoping you would actually do it yourself, but you have limited time as a student because you have a life, even though you shouldn't. You're taking my class. Your life should have been over. But yeah, so if you want to, you can read about this. Our goal today was to see there are practical applications of these things, as well as getting used to dealing with the math of these things with letters instead of numbers. So hopefully on test day, you're going to be able to handle circuits that have letters in them with no numbers. Got it? Now, for next time, look at page 125. And you can see that we're going to talk about these things called KVL and KCL. So for next time, if you want to read before class, read the rest of your resistor circuits. We're also going to get into RC transients. And then as you're packing up, I'm going to show you these plots really quick because I have them. So I'm going to get you can start packing up. I'm going to show the plots because I can't help it. I've got this video here. I just want to have it all in that one spot. If you got to take off, I'm not offended. But I'm going to get it in there so you've got it in the lecture that's recorded. What chapter is this? 27?
Sure.
What problem was that? 11? All right. And so I'll break these up really quick just so you can see it.
Yeah, I agree. I know.
Where's my Zoom?
Turning things around. I'm a visual learner, so well, I hate drawing, so I can see it in my head. That's the problem though, because I'm lazy with that, and then I mess up on stupid shit.
So there it is. If you want to see these plots, there it is. I'll just show you really quick. Again, I'm not offended if you got to go. I know some people have calc class. You can see these crazy plots. You can see all the tables that I made up there. And so if you're trying to do this, we're going to do some of this in lab this week. But you can see in particular, look how cool this green one is. I don't know why I like that. So this shows you the power delivered to each of these. And the idea is there's better and worse ways to do this. And if you're curious, once you make these tables, you could very easily change the resistance. And by changing this, the value of the long skinny wire, you could make this handle 15 watts or 150 watts or 135, and whatever light bulbs you had, you could make this by dialing in the resistance of the wire, by adjusting its cross-sectional area or its total length. You could make this work for a wide range of different devices. That's it. Stop the share there. Whew. You guys need a grade check? I'm willing to do